Okay, so this is laws of thermodynamics and change of state. So we're going to be going over phase changes for the first part. And basically, phase changes will occur whenever there is a separation in the chemical bonds between the particles of either the solid or liquid. And so what happens is all the energy that's going into the substance will end up being used to separate the chemical bonds between the particles. So then it will either gain energy to go from a solid to a liquid, from a liquid to a gas, or the reverse, where energy is taken away to go from a gas to a liquid, from a liquid to a solid. So as you can see on the bottom, there are the three states of matter, A being gas, B being the liquid, and C being the solid. You can see that the solid and C, they're tightly packed. They are pretty structured, whereas B is less so, and C and of course A is even less so. There is no definite shape. So again, in phase changes, the chemical bonds are either formed or broken as energy is being inputted or being taken away. So now, whenever there is a change in phase, the energies of the particles will change, but the average kinetic energy, which means temperature, will remain constant. So what happens now is that the amount of heat energy that's going in during a phase change, we call that a latent heat. And latent itself being, it means dormant or inactive. And we use that to describe how the energy is going in and doesn't have any apparent change to the object's temperature. So, but in reality, it changes the state of the substance. So here is a phase change graph, and the phase change graph, it's missing a little arrow up here, but this first part right here represents the solid, and then as the solid is increasing in heat, it is going to melt without a change in temperature. And then what happens as more energy is being used, what happens is the substance will then begin to heat up as a liquid, and it gets to some point, and we call this the boiling point. It will then start to evaporate until it reaches all of it has evaporated. Then it will start increasing in temperature again, but this time as a gas. So the latent heat of fusion is what we use, and that occurs when the object is melting. And over here is the latent heat of vaporization, which corresponds to the energy that is used to completely change the phase from a liquid to a gas. So some notable points on this graph is that this starting point is a solid. As it reaches the melting temperature, it is still a solid, but at the melting temperature, and then it will begin to melt as more and more energy is being used. And at this point, you have 50% of the mass as a solid and 50% of the mass as a liquid. Then, and when it gets to this point, it becomes 100% all water or liquid, and but at the temperature of the melting temperature. And the same process occurs over here at vaporization, where at this point it's all water at the boiling, or liquid at the boiling temperature, and at some midpoint it's 50% of the mass is a liquid, and the other 50% of the mass is a gas. When it gets to this point, all of the substance becomes a gas at the boiling temperature, and any more heat that we use to the substance, it will cause the gas to heat up. Okay, so now in the changes of phase, in terms of heat gain, here is a diagram of how the solid will go to a liquid, from a liquid to a gas, and from a gas back down to a solid. It can go in reverse this direction or go directly up through sublimation and deposition, whereas we have melting and freezing, and we have vaporization and condensation. So we have the enthalpy of system basically being that the heat content increases as you go from a solid to a liquid, from a liquid to a gas. So all of this requires the addition of energy to go from a solid to a liquid, from a liquid to a gas, or the release of energy from a gas to a liquid, from a liquid to a solid. So now when we look at this process, we are saying that by looking at this, how energy is required and needs to be absorbed by the liquid for the liquid to become a gas. We call that evaporation or vaporization. So we call that evaporation a cooling process, because as the liquid is absorbing energy from its surroundings, the surroundings itself, losing the energy, is going to cool down. So the environment gets cooler, whereas the liquid gets warmer. So evaporation is a cooling process because it cools down the environment. So think about the environment in which you are sweating. It's hot out, it's 90 degrees, you're sweating. The sweat itself on your skin is going to absorb the heat from your skin, which means that the skin is going to cool down, whereas the water, the sweat, is going to heat up, evaporating. So it's taking the heat away from its surroundings, the sweat's surrounding, to cause the surrounding, which is now your skin, to cool down, cooling you off, keeping you at a more comfortable and safer temperature. So then, of course, the reverse is true for condensation. As gases condense, it's going to be a warming process, because gas is going to release energy into the atmosphere, into the environment, for the energy to drop down from a gaseous state to a liquid state. So as the energy is released into the environment, it's going to be a warmer environment, which explains why after you take a hot shower inside a shower stall, because the steam is condensing, is releasing the energy inside the shower stall. And so it feels warmer than it does right outside the shower stall. So then, of course, we are going to talk about some examples where you have sublimation, where it goes from a solid into a gas, or from a gas into a solid. That process, sublimation and deposition, it skips the liquid state entirely. And some examples of it would be dry ice or mothballs. Okay. So a couple of vocabulary. Melting point. At this point, you probably already know what melting point is. It's a temperature in which it goes from a solid to a liquid. And a boiling point, which is the higher temperature. Generally, it's going to be a substance where it changes its phase from a liquid to a gas. Okay, so now when we are talking about energy that's being lost, when we are losing energy to its surroundings, the liquid to a solid, we call that freezing, and when a gas goes to a liquid, we call condensation. And it requires a loss in energy. That means the Q value, the heat content, is going to be a negative value. Because what happens is, as you lose energy, the particles slow down from a gas to a liquid, and then you move even more energy, the liquid will then slow down to form a solid. So then chemical bonds begin to form, and you have a situation where you have less energy. And we talked about condensation being a warming process. And so now, again, the heat is released into the environment, in which the environment temperature increases. Shower is one example. Other examples would be if you're going to freeze something, okay, energy is being released by the substance to be released into the environment. So generally speaking, the air temperature for, say, snow, when snowing, is a little bit warmer than when it's not snowing. So it's all relative. The temperature's all relative. So here are some review questions. We need to use the phase change graph to answer these questions. Temperature increase during melting. Number 2, is energy required for each phase change? 3, can both liquid water and steam exist at 100 degrees Celsius? What must be changed, temperature or heat energy during condensation? And 5, how would you describe the change and arrangement of the particles in the graph as heat energy and temperature increases? So it'd be a good idea for you to pause to answer these questions, and when you can, try to use answers that will have an explanation behind each of these responses. So here is the answers to the review questions previously stated, and this graph is basically another rendition of the graph you've seen before, except there's an extra arrow over here, and it's a pretty good summary of everything. So now the answers are here, but of course the why, the example given the questions here, does not tell me the why, but you should probably be able to respond with the reason. So more vocabulary. Now during a phase change, we know that the temperature doesn't increase. And when there is an increase in temperature, that means we're going to use the specific heat capacity equation. Q is equal to mc delta T. Now, when we're going to through a phase change, specifically at melting point or freezing point, we're going to use the equation, the latent heat of fusion equation. Now, what does heat of fusion mean? Heat of fusion basically means the amount of energy that is needed to melt 1 kilogram of a substance. So the equation is Q is equal to mHF. This only works for substances that can melt from a solid to a liquid. Now, the value mass is the substance mass, and HF is the heat of fusion for that substance. So it generally is a pretty constant number. The heat of vaporization is the amount of energy that's needed to vaporize 1 kilogram of a liquid. So if you're vaporizing something, that means you're going from a liquid to a gas. And when you do that, it's going to have a positive Q. But if you go in the reverse, where you're taking energy away from the substance, it's going to be a negative Q because the substance is losing heat. So Q is equal to mHV. HV stands for heat of vaporization. And again, just like the heat of fusion, it is basically a value that is a constant. So you can look it up. It's something that you can find if given the right resources. So then the added energy for these two equations, if you notice, does not include a change in temperature. So the added energy that goes into the substance will cause a change in state rather than a change in temperature. Okay. So now here we have the summary of the graph that you should know, and that is labeled A to B, B to C, C to D, D to E, and E to on. This will show you kind of like what's going on with the graph and the specific phases that this substance is undergoing. So you can look at the summary and be able to fill in your notes a little bit better. Okay, so what this graph basically tells you is that from A to B it is a solid, and you will use the specific heat equation for ice. And then from B to C, you would use the heat of fusion equation. C to D, you would use the specific heat of water equation. And D to E, you would use the latent heat of vaporization equation. And from E on, you would use the specific heat of water vapor equation. And where the slope of the line segment, where there is a slope, you would use that specific heat equation. And where there is no slope, you would use the heat, either heat of fusion or heat of vaporization. If you want to find out how much energy is required to go from point A to, say, point E on, you would find the heat of ice, the specific heat of ice equation here, find the Q value, then find the Q value from B to C using the heat of fusion, find the heat value for this line segment C to D using the specific heat equation, and then D to E for the heat of vaporization equation, and then whatever bit over here, another specific heat equation, and you add all the Q's values for all the 5 line segments up, and you have the total energy that's necessary to take a block of ice and then completely vaporize it. So here is a practice problem, and it'd be a good idea for you to try to do this on your own if you can make sense of everything that we've talked about here and also in class, so that you are able to make sense of it. The temperature is negative 20 degrees. Okay, to become water at 0 degrees Celsius. Make sure the units are correct. Okay, and it might be a good idea for you to pause here and then try to work it out. And then if you're able to, okay, get the answer. Okay, so here I have the solutions to the practice problem, and it's here. Q total is the total amount of heat. QW is the heat of the warming, to warm the ice to 0 degrees in the melting point, and then QM stands for the actual melting of ice to become water. So you would then warm the ice using the equation, specific heat equation, and then you will melt the ice using the heat of fusion. And once you get that, you sum them up, and you will have your answer. Okay, so this is going to stop here. Please make sure you do the web assignment. I will go over this question in class.